Swayam Prabha. Digital India. Educated India.
Thank you, Dr. Abhilasha, for the introduction and also giving me this opportunity to present this work. So this is the work of multi-criteria decision making for optimizing in gas allocation network. So this is done with a student, Gaurav, and myself. So as introduced, I am faculty in IIT Patna. So this is the outline of this presentation. We will look into the introduction, then the key issues of gas allocation network, then we will see a case study, then finally the conclusion. So as we all know, transportation of fluid is a very important aspect for process industry, especially for oil and gas. And transportation of fluid through pipeline is a energy intensive process. Hence, energy management is an important aspect for fluid transportation. Also, transportation of fluid through pipeline involves high startup cost. So, they have a wide application starting from oil and gas, fertilizer industries, water supply, and many more. So, these are the advantages. It has low rate, good loss and damage record. Pipeline can also function as warehouse and mostly unaffected by weather, and mechanical failures are also less. There are some disadvantages also. They have slow speed, we have fixed route, no door-to-door service, and these are limited to some limited commodities, and there are some geographical constraints also. Now, what are the key issues for gas allocation network? When we look for the gas allocation network, what are the key issues? So, one key issue is why obviously we want to save our resources. Resources are energy, mainly energy for transportation. That is, for gases it is compression, and for fluids it is pumping. Then other is capital investment. When we have to plan a pipeline, or we have to plan a pipeline or for transportation, we have to do a capital investment. Then there are some uncertainties. Integral uncertainties, what I mean to say that there are some uncertainties related to compressor. Sometimes compressors are available, or sometimes they are not available, under maintenance, or these types of uncertainties are always there. Some parametric uncertainties means their flow are varying, somewhere concentration likes, these things are varying. And other aspect is scheduling. When we have multiple product for a single pipeline, or two pipeline, 3-4 products. So these kinds of aspects we include in scheduling. And the aspect which we are looking in this presentation is multi-criteria decision making. There are, when we have to design a pipeline network, there are multiple criteria that we have to look, such as safety, leakages, geographical conditions. These are the multiple criteria we have to look. So how to take decision? So this is a slide I have put here for showing the uncertainty. The two kinds of uncertainty we see. One is parametric and other is integral. So I have discussed about this integral and or parametric. So how can we deal with these uncertainties? So one approach is stochastic. Stochastic mein we need the distribution. The distribution may be normal, log normal, or Chebyshev one-sided inequality, or any other distribution. Or other is the approach of robust optimization. Robust optimization is the approach where we actually immune our system from the such kinds of uncertainty. So how much we want to immune, we put in there. There are some formulations. We will also look into that also. And other is the integral uncertainty. Integral uncertainty can be multiple in multi-stage, because when we have to plan this time, and uncertainty we will face in some upcoming time in future. So these are the uncertainty which we face in multiple stage and multi criteria. Obviously, we are discussing this in this presentation, the multi criteria. So this is the slide. This work is also done. Actually, this is another work. So we have done this work. We have presented the Soester formulation, Bentonel formulation, and Bettis-Marson sim for gas allocation network, and this work is also published. Now, coming to the MCDM. So, introduction to MCDM method. It is a optimization tool for decision making, and a decision maker considers here more than one attribute. The aim of MCDM technique is to provide help and guidance to decision maker in discovering the most desirable solution, most desirable or most preferred. So this is the graph we can, this is a figure where we can observe we have some objective, then we have to understand the problem, we have to look what are the alternatives we have to evaluate the alternatives, then we have to choose our best alternative based on our MCDM approach, then according to we have to implement or take action. Again we evaluate our results, what are the results, or if we are not satisfied we again go back to our objective, and if we are satisfied it can be end. So these are some terminology I will use during this presentation. So one is goal. Goal means objective. Criteria we all know. Alternative, attributes, decision matrix, normalization, and ranking. So this actually figure shows for a car purchase problem, if we have to purchase a car, four-wheeler, the criteria may be cost, safety, comfort, and mileage. And we have alternative of 3 cars, car 1, car 2, and car 3. So we can actually give the intensity of importance to all these. 1 is for equal importance, 3 is for moderate, 5 is for essential and strong importance, 7 is for very strong, and 9 is for extreme importance. So here we can made a matrix according to this our importance. So cost to cost is 1, safety to safety is 1, safety to cost is 7, as we have given the intensity, and so on. So this is a matrix, 4 by 4 matrix we made. Now these are some traditional methods for MCDM. One is simple additive weight method, another is AHP, and the TOPSIS technique of order of preference by similarity to ideal solution, which we have used here, and elimination and choice expressing reality. This is electric method. So coming to this problem, what we have is we have the existing compression station, we have flow limits and quality, a set of compression station with specified quality, and we have demand. So every new compression station is associated with predefined criteria. So we have to find out which new compression station is to be installed. So the present work aims to determine the optimal gas allocation network of process route which represent the most satisfied solution for all criteria. This most satisfied solution provide unique solution with maximized benefit and minimized risk under energy constraint scenario for achieving optimal gas allocation network. So these are the equation. This is the flow balance. Obviously the whatever we have in source, we have to satisfy the demand. The second equation, Then quality balance, if there is some quality we have to maintain in demand, so this is a quality balance. And these are the compression energy requirement. So for isothermal, for polytropic, it is written as a, in terms of a energy index. Now this is the methodology. So the two lines of methodologies are showing. One line is for TOPSIS and other line is for pinch analysis. So for TOPSIS, we we construct a decision matrix with M alternatives and N attributes. For normalization, then we normalize, then we create the weightage of output responses, then weighted normalized matrix is created. We calculate the positive and negative ideal solution. I will show in next slide this, what is this, and we separate the positive and negative, and then we calculate the closeness coefficient, and accordingly we rank. Then next we do pinch analysis. We plot a limiting composite curve for existing compression station. Some compression stations are existing. We plot a limiting composite curve. Accordingly, we identify the pinch point. Okay, and then we determine this MCPFI. So this is the multi-criteria prioritized factor for each new compression station. Then we introduce the compression station with increasing order of MCPFI into the LCC, and the flow is calculated using the methodology. This paper has a set methodology, a established methodology for calculation of flows. So, and then we finally tabulate our results. So next is this is a typical one of the example I have considered here, where we can see these are the flow limit, compression energy index, then the quality, investment and leakage. There are three attributes: quality, investment and leakage. So accordingly we construct a decision matrix, then we normalize this decision matrix. Further, we determine the ideal best, anti-ideal, then separation of this ideal and anti-ideal is done. Then we calculate the relative closeness using this equation: C star is equal to S star divided by S star plus S dash. So this value of C star provides us the ranking. Now once we get the C star, we calculate the MCPFI, multi-criteria prioritized factor, which is actually dependent on the pinch quality. So we have to construct the limiting composite curve and then flow line. So where the limiting composite curve and flow line touch, the point of contact is the pinch point. So using this pinch point, we calculate the MCPFI and then arrange our new compression station accordingly. So okay, so finally the conclusion. So developed model provide an extension to TOPSIS, which is integrated with pinch analysis. So inclusion of multi-criteria aspect mitigates the issue of numerous domain of gas allocation network, and it is observed, or it is reported that addition of a new compression station is optimum if and only if its MCPF is positive. First condition is has to be positive, and second condition is has to be less than the remaining new compression stations. So this, the most satisfied solution provide the opportunity to minimize the cost and energy simultaneously. Finally, I want to acknowledge Sir for giving me the fund, and also I want to acknowledge my PhD students and PSC lab members, Alkuma, Manish, Rahul, for their help. This is our lab, one pic from our lab. So thank you.
Okay. Thank you, Dr. Dutton. So, any questions? Those who are sitting here? Any online questions do we have? Okay. So, I have one question. Can you go to the constraint slide where you are mentioning the constraints for... Yeah. So, this quality constraint, this is what quality? I could not understand that.
Quality means if there is a in demand, there is a concentration limit. So this should not cross a concentration limit. So that is the quality concentration.
Okay. So, do you mean that when you transport the gas through pipelines, is there some contamination, or how does this
If it
concentration
is a local
changes?
network, so let's say it is a hydrogen allocation network. So there is some purity we have to maintain in demand. So that is kind of thing.
Okay.
It can be addressed, and if it is not, we can go with the other quality. If it has to be there, we can include this.
Okay. Now, I was just trying to understand why this quality gets changed in the network. What are the factors that are responsible for this change?
It does not change during the transportation. It is actually from the sources. We have the sources. Some sources most pure, 90% pure. Some is 80% pure. So while mixing or something like that, it.
Okay, so it's kind of a blending problem, but it does not changes during transportation.
No.
Okay, because in case of water distribution networks, the water quality changes
Yes.
due to contamination and so many things.
Yes. Okay.
Okay, thank you very much.
Thank
Yeah.
you. Thank you.
So moving ahead. The next talk is by Muhammad Umair Iqbal from IIT Gandhinagar. He will be presenting on EEG based approach for cognitively characterizing the performance of control room operators. So your time starts now. Go ahead.